Hello, welcome to the Bakwas channel for self-paced tutorials on Internet of Things. This video illustrates basic object detection using the UNIHIKER single board computer from DFRobot using YOLOv8 software from Ultralytics. UNIHIKER is a single board computer from DFRobot with two tightly integrated processing systems, a Debian Linux platform and an Arduino-compatible microprocessor platform. YOLO, you only look once, is a powerful and versatile object detection algorithm for applications in self-driving cars. YOLO can be used to detect objects on the road, such as pedestrians, vehicles, and traffic signs. Surveillance systems. YOLO can be used to monitor for suspicious activity or objects in surveillance footage. Medical image analysis. YOLO can be used to detect abnormalities in medical images such as tumors or lesions. Robotics. YOLO can be used to enable robots to perceive and interact with their environment. UNIHIKER is a versatile Internet of Things solution from DFRobot. It is a single board computer for Internet of Things and educational applications. It has two primary interfaces to support Debian operating system and Arduino microcomputer systems. The UNIHIKER offers a wide range of solutions for developers and hobbyists. This tutorial will limit the focus to a basic demonstration of object detection using computer vision interfaces supported by OpenCV. But before we do that, let's take a sneak preview of the hardware. Coprocessor offers efficient communication with various analog, digital, I2C, UART, SPI sensors, and actuators. Wi-Fi and Bluetooth connectivity enables wireless communication and integration with other devices. Built-in sensors includes a light sensor, accelerometer, gyroscope, and microphone for sensing the environment. Touchscreen provides a user-friendly interface for interacting with the device and visualizing data. Onboard microcard storage. Of course, you'll have to buy the microSD card yourself. Pre-installed storage comes with pre-installed software, including a Jupyter Notebook environment for easy programming and data analysis. Python support provides excellent support for Python programming, making it accessible to a wide range of users. IoT capabilities. Built-in IoT services allow for easy data storage and access through a web browser. YOLO, you only look once, is a very fast vision processing solution for object detection. The first version was launched in 2016 by Joseph Redman and Ali Farhadi at University of Washington. The solution has been extended to version 10, with version 11 to be widely available soon. Our demonstrations in this tutorial will use YOLOv8 from Ultralytics. YOLOv8 is being used currently by yours truly to prepare tutorials running on diverse platforms such as AMD 64 for desktop examples where it shines brilliantly, ARM 64 for portable solutions with a Raspberry Pi 5 hardware that may not be an optimal solution for some, but cannot be ignored for evaluation purposes. This tutorial is based on the documentation and tutorials provided by Ultralytics, who develop, maintain, and support open source software and tools related to object detection. Their YOLOv8 model is considered one of the most advanced and efficient object detection algorithms available. It is sincerely hoped that you will browse the Ultralytics website and learn much more than my simplistic efforts here. Their community forum site is excellent for persons practicing object detection at all levels of expertise. This tutorial does not cover the architecture of YOLOv8. I don't have that level of expertise as a beginner in the subject. Please visit the Ultralytics website for more in-depth technical information on the underlying technologies. There are so many parameters in YOLOv8 that it would really be impossible to present demonstrations of even the key parameter at any meaningful level. I have chosen the key topic of object detection and then extended the demonstration to counting the objects. I feel that it is important to apply YOLOv8 for your applicable projects and then evaluate the results. This approach will help you to ramp up the YOLO learning curve at a much faster rate than trying to digest the underlying subsystems in YOLO. You may have noticed all the popular machine language packages that are considered as prerequisites and installed when installing the base Ultralytics package. That alone should help you to appreciate the incredible foundation behind YOLO. It is best to create a virtual environment for the exercises since Ultralytics recommends Python version 3.11 or later for the package. VNV and Conda are two popular examples of virtual environments. The demonstrations on the UNIHIKER use the Conda framework. After creating a virtual environment and activating it, use pip to install the Ultralytics package. This step will ensure the long list of prerequisites are installed too. As you will see in the demonstrations to follow, there is a long list of key packages that are required for YOLOv8 to work properly. For the sake of completeness, here are two Conda commands that may be of interest. These commands were not used in the current demonstration. The first command deactivates the virtual environment using a command instruction. Similarly, Conda can install packages too. The example on the slide is for the Ultralytics package. The demonstration in this tutorial used pip, which is part of the base installation for Python. Similarly, one can use VNV to manage virtual environments as it is part of the base Python package. However, I chose to illustrate that Conda can be used in UNIHIKER too. Ensure that the correct virtual environment has been activated, whose name is prefixed with parentheses as the leading string of the command prompt. If you are using Conda to manage your virtual environment, review the preceding slide on how to enable and activate the virtual environment. Use the pip command as shown on the slide to install the Ultralytics package. This process takes a few minutes owing to the number of very large packages that are installed. After the installation is complete, it is always a practical suggestion to validate the installation. Ultralytics provides a very simple command line for this purpose. The format for the command line entry is YOLO, task, mode, args, where YOLO is the name of the command, task is optional and can be one from the list: detect, segment, pose, or OBB. If it is not specified, then the program will guess the task from the model type. Mode is mandatory and can be one from the list: train, val, predict, export, and track. Args is optional and can be any number of space-delimited keyword value pairs with an equal sign. In our example, the model and image files are specified as args. In this example, bus.jpg is assumed to reside in the current folder of the virtual environment. Ultralytics does provide an image with the same name at its website. Key considerations when choosing a model: speed. If you need near real-time performance, consider smaller models like nano or small. Accuracy. If accuracy is the most important factor, choose a larger model like large or experimental. Hardware. The capabilities of your hardware, CPU or GPU, will influence your choice. Larger models may require more powerful hardware. Use case. Consider the specific requirements of your application. If you need to detect small objects, a larger model may be necessary. It is recommended to experiment with different models to find the best fit for your particular use case. You can easily try different models using the Ultralytics library and evaluate their performance based on your criteria. This tutorial does not cover the architecture of YOLOv8. I don't have that level of expertise, as I still have a lot to learn on the subject. Oh, this is not right. The demonstrations in this tutorial are limited to illustrating a few basic operations with YOLOv8 running under UNIHIKER. It is important to remind ourselves that the UNIHIKER has limited resources but is fully capable of running basic YOLOv8 models. It is simply that running programs on the UNIHIKER will take a little more time since there is no GPU to provide accelerated support. The demonstrations will illustrate the basics in object detection and object counting. Segmentation is an important facet in ensuring that all objects in the input are fully detected and counted. It may be necessary to provide a separate tutorial on this subject. It is important to understand the different modes supported in YOLOv8 to gain the maximum benefit from the models. These modes are train mode, to fine-tune your model on custom or preloaded datasets. Val mode, a post-training checkpoint to validate model performance. Predict mode, unleash the predictive power of your model on real-world data. Export mode, make your model deployment ready in various formats. Track mode, extend your object detection model into real-time tracking applications. Benchmark mode. Analyze the speed and accuracy of your model in diverse deployment environments. Our focus in this introductory tutorial will be on making predictions using an existing YOLOv8 model on our images and videos. The results will be overlaid on the input but saved separately, as well as displayed on the console window. Summarizing the classes and locations of objects detected and/or counted. Some of these other modes, especially train and track, will be demonstrated in future tutorials. The predict mode using existing models is very simple to use. The command line version of this mode was demonstrated in the validation test after the deployment of YOLOv8. We will demonstrate two Python scripts with the same single input image file for both scripts. The first script will be run in two modes, without and with visualization. The script has only two statements apart from the import declaration. The first statement loads the specific model. In this example, the model is the nano model YOLOv8N. If it is not present in the folder, then it is retrieved from the Ultralytics website. YOLOv8N is the smallest model. It has a fast inference speed and is best suited for the UNIHIKER, which has modest hardware resources. The second statement runs the object detection using the specified image. In the second script, all available Ultralytics models are compared from a performance perspective with the same input image file. Again, there are many options to customize the output results. We will demonstrate only one simple example for this purpose. Here is the Python script that we will use in the initial demonstration of the predict mode. After loading the YOLO library, two statements are executed. The first statement loads the model. In this example, we are using the standard Ultralytics model of the COCO dataset that is very popular for object detection applications. This particular model, the Nano YOLOv8N, is suitable for low-power devices. When you have trained your own model, you can substitute the model name as the parameter. We will cover the training of user models leveraging YOLOv8 pre-trained models in a future tutorial. The second statement invokes the model function using the name of the input file as the only parameter. There are many options for the input parameter even with this simple example, but in order to keep the demonstration simple owing to the resource limitations of the UNIHIKER board, a JPEG file is specified as the input source. Ideally, the input file should have a resolution that is a multiple of 32, but for demonstration purposes, that requirement can be relaxed. For this demonstration, however, the input file has a resolution of 640 by 640 pixels in height and width. This short tutorial demonstrated the use of vision processing for object detection and counting. The demonstration platform was the DFRobot UNIHIKER hardware with the YOLOv8 package by Ultralytics as the core processing component. Obviously, using the UNIHIKER board should be limited to special applications for object detection owing to the limited resources available. However, the fact that YOLO can be run on UNIHIKER is a great testament to its design as well as the tremendous work done by the software package publishers who generously provided an open source solution for all of us to improve our learning experience in vision processing. So before it proceeds to installing all the prerequisites, it's asking for the confirmation information, and I'll just go ahead and press Y to let it proceed. Let's log on to the UNIHIKER. YOLOv8 can be invoked from different platforms. There is even an Android app too. For the limited purposes of the development exercises in this demonstration, we will use Python script. Python script suits our introductory needs in a more flexible manner. So we will rely on Conda to create the environment for running Python. And we already have mini Conda there. So we can now go ahead and create a working directory for YOLOv8. And it exists. So we change over to YOLOv8 and we run the Conda command to create the virtual environment. And we specify the specific version number of the Python interpreter. And it's going to go and start its work as soon as we confirm that we want to remove the existing environment and update it with the new environment. It'll proceed, and I'll stop the video and come back when the operation is complete. And after a few minutes, the installation is complete, and we have Conda installing the virtual environment. So now we can go ahead and use pip rather than Conda, but before we can do that, we need to activate that environment. So the command for that is Conda activate YOLOv8. There we go. So now that's done, you can see that the information has changed in the prompt, and we go and launch pip install Ultralytics. And once again, I'm going to stop recording the video and come back when the operation is complete. So the installation is now complete, and we will proceed to testing the installation of the Ultralytics package. So I'll just do a very simple interactive test by importing the Ultralytics package, and if it loads correctly, then we'll know for sure that the package has been installed and we can proceed with the hello world type of demonstrations. So since it's taking a little longer, that is a fairly healthy sign that it's going through the packages that have to be installed in conjunction with Ultralytics and validating it, like Matplot, for example. And obviously, it's a good sign that the package has been installed correctly. So let's give it a few seconds, and then we'll get the response back, and we'll exit out of this mode and proceed with the actual demonstration of the simple hello world exercise using built-in YOLO V8 model. So you can see that's the message that everything is fine, and then I just type in exit and just get out of it. And so we're done, and now we can proceed with the demonstrations. Let us work on a very simple basic test of the YOLO V8 model. So we'll go ahead and create a working directory here. And I'll just use nano, and I'll call it basic test.py. Okay. And obviously I love to make sure this is not necessary, but just old habits die hard, as they say. So I'll go ahead and import some code that I already have, cut and paste it in here, and just line it up properly. So bottom line is that in here, so and as you start using YOLO V8, what I'm doing here will become second nature to you. This is the most fundamental test that we can do. So just close it, run it, and now we can go ahead and see what it does. Basic test, and it's using files straight from Ultralytics YOLO V8 repository. So Python's going to go ahead and do its thing, and it's going to pick up the bus, the famous bus image, and tag it for us with the objects that it has detected. So it's going to take a while. I'm going to stop the video, and then I'll come back when it's done. So here it's downloading the model, and then now it's going to go ahead and get the COCO dataset in. And obviously, if you're familiar with COCO, common objects in context, then there are about 80 labels that it'll search through and train it. And left it as the default 5 epochs. So it's going to take a while. I'll stop the video again and come back when there's some more meaningful information to share. And now we're on to the number crunching stage of the 5 epochs. So obviously this example didn't work, and now I'll have to try some other simple example. Let us now look at a very simple Python script to illustrate the predict mode. So we just call it predict.py, and we will scroll down to the 3 key statements. We import the Ultralytics library package, the YOLO component. We load the model. This is the Ultralytics YOLO V8 smallest model that is suitable for the UNIHIKER. And then all we have to do is take the object and pass it the image that we want to use for detection, and just run it. So 3 statements, and we're done. Now that we've had a chance to look at the 3 statements, let's go ahead and run the script. So the file is predict.py, and we can just run that. And as you can see, it found 6 chairs, 3 dining tables, and 5 clocks. And it summarized the speed information, the pre-processing time, the inference time, post-processing time per image. Now that we have tested a single model, let's go ahead and test the same image with all the available YOLO V8 models. And I have this file called predict2, and we're going to run there and print out more information So I've said save equal to true, and it'll give us all the processing that it is doing while going through the detection. So let me get out of this. And now let's run predict 2 in the same manner that we did for the other one. So we'll launch it with the Python interpreter. So the program is now going to go ahead and provide information about the intermediate steps. And as you can see, after it did the calculation, it saved the results in the folder called runs detect predict 9. So I also have another file called compare.py. Let us go ahead and look at this briefly before we run it. So as you can see, we have the YOLOv8 which we've just tested. We have the YOLOv8s, the YOLOv8m, and YOLOvL. I've left out the X because the resource requirements are too extensive for the UNIHIKER. So we're going to go ahead and run this, and essentially what we're going to do is print out the intermediate information. So let me get out of this and then run. So let us go ahead and run the script. And in this case here, as each model runs through, some summary information is presented, and at the end of the run, a comprehensive list of all the boxes and the confidence factors that were estimated will be provided. As you can see, as the models become bigger, the times required for pre-process, inference, and post-processing all increase correspondingly. So now we're getting the information about the boxes and the confidence factors for each of the models. And while it's great to have this level of detail, perhaps a picture is worth 1,000 words, and I'll go ahead and show you the results from each of the models as saved images. I'd like to show you the model files that are downloaded from YOLO. So you see these files in here, YOLOv8L, YOLOv8N, YOLOv8, and M. They all have the extension .pt. PT presumably stands for pre-trained models. So if these files don't exist in your folder, then they are downloaded from the Ultralytics website. And that generally happens during the first run, and you don't have to do anything. Thereafter, you save a few seconds by not having the need to download these files. So once again, when you create your own custom models using the YOLO pre-trained models, you'll have a similar set of .pt files in your working folder that you will invoke as the model file. Let us review the performance data from a qualitative perspective. Using a single JPEG image file as the input, let us run the object detection exercises with all 4 YOLOv8 models to gain an understanding of the performance. The three basic phases in YOLOv8 object detection are pre-process, inference, and post-process. The four YOLOv8 models under consideration are YOLOv8N, commonly referred to as the nano model, YOLOv8S, the small model, YOLOv8M, the medium model, and YOLOv8L, the large model. The model data size increases from nano to small to medium to large. However, there is no predictable trend in the pre-process phase with the chosen JPEG image input file as shown on the slide. In the inference phase, however, the trend in processing time is quite clear, with the nano requiring the least time and the large requiring the largest time. However, this visualization needs to be understood in the context that there were false positives and false negatives with some of the models. Hence, conclusions can only be drawn after developing the confusion matrix, which is not in scope for this tutorial. In the post-processing phase, there is a trend after the nano model is run, which takes more processing time than the small and medium models, but less time than the large model. Of course, the overall trend is almost similar to the processing phase simply because the time required for the processing phase is significantly longer by 2 orders of magnitude than the pre- and post-processing phases. Since we get a qualitative idea of the resource requirements for the models, we should be careful to use the most appropriate model based on the resources available. Here is a quick summary of the results for the first test image. In the nano model, the elephant confidence is only 0.59, and the two persons in the top right-hand corner were not detected. In the small model, the elephant confidence improves and the distant persons are detected. In the medium model, the elephant confidence improves further to 0.92, but a partial bamboo tree on the ground is falsely detected as a kite. In the large model, the elephant confidence decreases slightly, but the confidence values for the persons increase. Although the runs display the processing time, these are not being examined in any detail except to understand that the nano model is the fastest and the large model is the slowest. In the second test image, it should be noted that the statue of the dark person is only detected in the medium model. It is not detected in the nano, small, and large models. Obviously, this is a flaw in the development of the pre-trained models using the COCO dataset, which is the basis for the pre-trained models in many object detection algorithms. If one encounters such a situation in the real world, then it is worth spinning the extra cycles to train one's own custom model where the YOLOv8 pre-trained models can serve as the starting point, or alternatively, another commonly accepted model can be used. I hope that this simple example illustrates the importance of data engineering, as it is called in machine learning, in ensuring that the training and validation datasets span the range of image data that will be encountered in testing or production use. This is a very important consideration in machine learning, that the results can only encompass conclusions from the training dataset. Beware of fake AI salesmen. This short tutorial demonstrated the use of vision processing for object detection and counting. While the UNIHIKER may be able to run all the basic ultralytics models, the hardware resources are constrained even for the nano model, YOLOv8N. Obviously, if real-time processing is not an issue, then one can use UNIHIKER as a low-cost solution with suitable resources for input data in vision processing applications. That's all, folks. Thanks for taking the time to view this presentation. Would love to hear from you with your feedback. You're always welcome to be critical in any which way you can. Until the next time, bye for now. This presentation was prepared with assistance using free open source software, FOSS, from Ultralytics for YOLOv8 and their excellent community forum for support. And for the backbone of this presentation, from Debian, Inkscape, OBS Studio, Kdenlive, LibreOffice, and of course Ubuntu. The hardware was from DFRobot. Teachers, viewers, and peers provided valuable feedback. My apologies if I have inadvertently omitted anyone from this acknowledgement. A very big thank you to y'all for the assistance.